might joins, I wanted to talk a little bit about some of the readings that are coming up. So the one you did for this class, if you had a chance to look at it, and then a few others are going to be taken from annual reviews. So I've put my PDF versions of these, so they have my highlighting. I'm sorry, normally you'd be able to be on campus and download your own, but since I don't know how accessible some of these are, I wanted to put my own up here. So, but just annual review articles are really nice resources to turn to if you want kind of a general overview of the state of any field. So there's a ton of them pretty much on any subject. Just they get a few experts to give kind of a summary of everything about that subject and then write it in a longer paper. So they're a good place to start if you are looking for a very thorough, complete analysis of any field. So that was the Kennicott and Evans 2012. This is an annual review article to kind of get an idea of what that is. And then also this one down here, Hollenbach and Thielens, should have an S, sorry. That's another annual review article just to, so you get an idea of what sort of information is out there. We're also going to have a few days where we're using NED level 5. So that's what these are. They're readings from NED level 5. So NED is the extra galactic database. I forget what N stands for. But you can look up data on galaxies there, and then level 5, they just go through and they get experts to write summaries that are a little shorter, a little more user-friendly than an annual review. But it's another really good place if you're looking for just kind of a general set of information about anything. So that's a lot of what we're going to be reading from now on will be either NED level 5 or sections of annual review articles. And I will try to always make sure I have a PDF of the review article up in case you can't download it. Not sure if you guys have seen, if you've seen or used NASA ADS, this is how you usually download articles, and you can say, I want everything where Kennicott, Rob Kennicott is the first author, and that was written in 2012, and it'll give you this paper. But right now there's some issues just because if you're not on campus, you might not be able to download this, and that would be frustrating, so we're not gonna worry about that too much. Anywho, so that's kind of the basic layout of the reading. Usually there's a book that gets assigned to this class. I have had 2 classes with that book. I've opened that book maybe a grand total of 3 times. So I didn't want to tell you guys to buy something that I have not read any of. So that's why I'm doing this instead, just as a heads up. Today we're going to be talking about my favorite subject, which is measuring star formation rates in galaxies. So we're going to kind of walk through how we do that, what we might look for, and then there'll be an opportunity for you all to measure a star formation rate in a galaxy. So that's kind of my plan for today. First, I just want to give you guys a minute, either throw something in the chat or shout it out. What should we look for if we want to find a signature of star formation? What might be a sign that there are young stars in a galaxy? So see blue, yes, we've talked about blue light. Blue, dust. Dust makes things tricky, we'll talk more about that. But yeah, a lot of blue. Any other ideas? Maybe I'd like rephrase this a little bit. What kind of stars should we look for? On O-type, that's yes. So we'll get to that. Hot stars on main sequence, on early main sequence. So yeah, those were kind of my 2 ideas. So there's 2 things to think about. You can think about the 0-age main sequence, where stars, before they evolve, they kind of drop down slightly below the main sequence, and then they move up a little bit as they come onto the main sequence. Unfortunately, it's kind of difficult to spot differences between main sequence stars and 0-age main sequence stars. So this is something that's not usually, it's difficult to measure stars on the 0-age main sequence because they look sort of just like cooler stars on the main sequence. So that can be a difficult thing to find, especially when you're looking at just the total light from a galaxy instead of individual stars. So instead, like Ethan said, we often look for O and B type stars because O and B stars do not live very long. So if we can find signs of O and B stars, we know they had to have formed in the last 10 to 100 million years because O and B stars die in 10 to 100 million years. So that's kind of the main idea of measuring star formation rates, is that we are looking for some indicator that there are O and B stars present. Again, because if there are those O and B stars, they must have formed 10 to 100 million years ago, and that's recent enough that we can say that there is recent star formation. Again, we're kind of working on astronomical timescales, so what is recent becomes a little, you know, 100 million years. Sure, that's close enough to now. And again, you kind of already got this. I saw the blue light. If we are looking for O and B stars, we want to look for blue light. That's true. Also UV light. Pretty much any of that high energy light is going to be almost all from O and B stars, because even though there won't be many of them, they put out so much of this light and so much more than any of the other stars that pretty much all of the blue and FUV light we see in a galaxy is coming from O and B stars. And just to kind of highlight this again, I've put the spectra of a few different classes of stars over here. And what we can see is that the fluxes you can kind of ignore because there's not actually a scale there, but the O and B stars have this kind of UV and slightly blue light that just doesn't get emitted by A, F, J, K, and M stars. So anything lower, especially when we get to the kind of solar type stars and below, are not emitting very much UV. They're not emitting very much blue light. So we know that most of our blue and FUV light is coming from the O and B stars. So to measure star formation, we're looking for young stars. Zero-age main sequence is hard to get, but O and B stars we know have to be young because they don't get old. So if we can find them by looking for UV and blue light, we have found recently formed stars. So let's say we measure our FUV luminosity, LFUV. What else do we need to know if we want to turn LFUV into a number of new stars formed recently? So kind of other words, in this equation that I've written here, kind of general equation, what would go into a theoretical prediction of M and B? If you have an idea, you can throw it in a chat or shout it out, whatever. Any thoughts?
I would assume that the M is for mass.
So no, so these are just like slope and intercept. So this is just a line fit. Like if we want to say, what do we need to, how do we convert FUV luminosity to a star formation rate? Sorry, maybe that's a better way.
Like how bright a hot blue star is, like the ratio between luminosity and number, I guess.
Perfect. So that's my next slide. You got me right to the perfect slide, Thomas, thank you. So the first thing we need to know, is how bright is one O star? Or, a few O and B stars. And so this is an image from one of my grad textbooks. But the idea is that we can take, if we know that an O3 star has a luminosity, an FUV luminosity of 10 to the 8 times 10 to the 5th solar luminosities. Or you can also look at it, this is another way it's often listed, is the number of Lyman continuum photons, so NLYC. This will come up again later when we talk about H2 regions, so don't worry about it too much now. But if we can convert our FUV luminosity into a number of O and B stars, that'll be step one. So now we have, instead of an FUV luminosity, we have a number of O and B stars. Is there anything else we're gonna need to know? So if we're forming O and B stars, what else are we forming?
Would we be forming H2 regions as well?
So they're forming in H2 regions. So we've got O and we have a number of O and B stars. If we have a certain number of, or I guess are O and B the only type of stars forming? So if we know our number of O and B stars that formed recently, we also want to know how many AFGKM stars formed recently. So we'll need to know, this is where we bring in something called an initial mass function. So that's, if 10 O and B stars formed, then that means 100 K stars also formed. And so this is just kind of a prediction of how many differently mass stars, initial mass function. So when we initially formed our stars, how many of every mass were there? And I like to kind of represent this with a broken plate. I think I get this from Andrea. But the idea is when you break a plate, you maybe will have a few very large pieces and a lot of really small pieces. So we have maybe 2 O and B stars, but a ton of K dwarf stars. So we need to be able to know, or at least model, how many lower mass stars there are once we have our measurement of really large stars that formed recently. So these are just a few versions of the initial mass function. Depending on which model you're using, you'll use a different one. Mostly people hear people talk about the saltpeter, the Krupa, and the Chabrier, I think it's French, sorry, models. And so the saltpeter is kind of the initial model that says your number of stars, which is written as a C, I think, as a function of mass, is proportional to mass to the negative alpha. And alpha is usually set to 2.35. So I think that's negative alpha is negative 2.35. So we get this, there aren't going to be very many high mass stars, but there will be a lot of low mass stars. The Krupa, and so that's this blue line here, is just a nice linear, when you do it in log space, slope, where we can see a lot of small mass stars, not very many high mass stars. The Krupa and the Chabrier are similar. They just kind of add in some version of cutoff masses. So it says, don't keep going to infinity for small masses. Essentially, we're going to say at 10 to the, or at 0.5-ish solar masses, this is going to turn over or it's going to stop or something. So the Krupa, you can see it gets kind of flatter as you go to low masses. It doesn't stay linear in log space. And same with the two different Chabrier, where we're just turning over. Once we get under 0.5 solar masses, we're saying we're not going to have infinite LTY dwarfs, because that wouldn't be good. At some point, you're going to turn off. There's not going to be any lower mass stars. There'll be some number that will kind of turn off your star formation. So we looked at our galaxy. We measured FUV light to measure the light from O and B stars. and we used our conversion from FUV light into a number of O and B stars to get a number of O and B stars formed recently. And then we can plug that into our initial mass function and say, if this number of O and B stars formed recently, this number of total stars formed recently. Pause there. Does anyone have any questions? So this got brought up a little bit, but what's going to be the major issue if we're measuring star formation rates this way? What's going to block?
Trusting the IMF.
Sorry, can you say it one more time?
I was saying trusting that the IMF is like a good proxy.
Yeah, so there's going to, no matter what we do, there's going to be error in our models. So that'll be a big problem, but it's also the best we can do. So the IMF does insert some uncertainty. What's going to be an observational limit, I guess? What's going to block O and B starlight?
Like dust scattering UV.
Yes. UV light is very short wavelength. Dust is really good at blocking UV light. So in order for stars to form, you need, stuff for them to form out of. So gas and dust, as it heats up, that's that gas and dust, it's good for forming the stars, but once the stars form, the light from them will get blocked. And especially the UV light will get very, very blocked by dust. So this was just kind of a little visualization of that. Our O and B stars are going to be forming in these nebula. The blue light will get absorbed and red light will be re-emitted often. So especially UV light, optical light will also get blocked by dust. But the dust also radiates as it heats up. So dust that's absorbing UV light is hot because anything that absorbs light heats up. And so it will also radiate in the infrared. So what often is used instead of just using FUV is we'll use something called a hybrid star formation rate indicator. So we'll correct for the dust observation. We'll correct the FUV for dust absorption by using IR measurements as well. So often what you'll see used for your star formation rate indicator will look something like this. We'll take our observed FUV light, we'll correct it by adding the 24 micron or some other infrared indicator, often 24 micron, and that's what we're going to do, multiplied by some factor to get an intrinsic FUV flux. So this is all assuming we know how dust absorption works, assuming dust absorption works about the same in every galaxy, which, and then it's also assuming that we can model it well with the 24 micron light. And so then once we have that, we can plug, our C has all of our kind of physics inside of it, and we can plug our intrinsic FUV light into an equation that looks like this to get a star formation rate. And I really like this image of the Whirlpool galaxy looking in different wavelengths. So HST, that's optical. Galax is our FUV, not infrared. And then the rest of these are all Spitzer and Herschel infrared measurements. And you can really see that what's bright in the infrared is not necessarily what's bright in the UV. So especially like this big something or other right here could be a really dusty star forming region that doesn't show up very well in the FUV, but does show up really well in 24 micron. 24 micron is pretty much always hot dust. So that's a good sign that there's hot dust. It's a really good proxy. We'll talk about this more when we get into the multi-wavelength Milky Way next week, 2 weeks from now. but different wavelengths of light represent different things. 24 micron is almost always an indicator of hot dust. So we can add that back. We can add the light that was absorbed by the dust by looking for infrared light emitted by dust that's emitting as a black body. And that's exactly what we're going to do. We're going to use that kind of basic formula. It's in this reading in tables 1 and 2. So we have our C's kind of in there, and then the correction factors are in table 2. So you'll need to use both of those to get your star formation rate calculations. This is another of our assignments. So this is going to be another little coding project. It's in day 6. I'll note that there's 2 images, one for 24 and then one for FUV that you'll need to download so you can do some aperture photometry on, just making sure that was the right notebook, on the fireworks galaxy. I was also able to get a version of a notebook working that works without photutils. So if you downloaded Anaconda, got your notebooks running, but you didn't do you couldn't get through the steps to get Python 3.5 or 3.6 working with photutils, this is an option that'll get around that. It's a little messy. But what you should see, let's see, this might be, okay, yeah. So the only difference is in this version, you get to work with a slightly ugly function I made that does the same thing that photutils does. So this is the no photutils version. But once you get these downloaded, you should be able to run the code that I've gotten written. And then there's a step for you to perform where you extract the 24 micron flux. So my thought is kind of based on, there's one thing I should note. I think I say the 24 micron image is in millijanskys somewhere. It's in millijanskys per steradian. If you need help converting that, I will be here. My thought is that I'm going to open one Evans book. I'll point out also, this is in your files. The solutions are all in your files, and they should be accessible now. So if you go to Files, Star Formation, Jupyter Notebook, Star Formation Rate Measurements, one of these has the solutions. And I'll put it in the assignment for today as well once I get the video finished. This is another one where I'm going to encourage you to, if you have questions, let me know. We are running out of time, so there's a few things I wanted to hit on before we finish. But this aperture photometry is essentially your photometry project. So this is what you'll be doing with your UGRIS data. So everything that's happening kind of in these 3 steps is pretty much what you need to do. So if you don't have photutils working, you can still use my funky aperphot and it'll do the same thing pretty much. It's very slightly different, but that's another option. But either one of those 2 things, this is how we can get to do aperture photometry, which is essentially, putting a circle down on your image and just adding up all the flux values within that circle. So that's what aperture photometry is doing. We're saying, here's our data. We defined a circular aperture with a 10 arcsecond radius centered on the nucleus of our galaxy, using specific coordinates that are in the header. And then we can add up all the fluxes inside of that circle, or all the pixels inside of that circle. Just really quickly, there are a few other ways besides FUV and 24 that you can get star formation rates. You can use radio emission. So radio emission mostly comes from either free electrons bouncing into each other, or synchrotron emission from electrons spiraling around magnetic fields in a galaxy, but all of these electrons are going to come from ions that were usually photoionized by young stars. Some of them also come from supernova, so there is a bit of what you're measuring is stellar death, but if the stars are dying, they had to have formed fairly recently because the only stars that go supernova are those O and B stars. So that is another potential way to get star formation rates, is to look for radio light. The nice thing about radio is super long, no extinction. The big con to radio observations is that it's difficult to do. Radio observatories you need huge detectors, you need arrays, so it's observationally costly. And this is just kind of showing radio light. Backwards, I have to remind ourselves, this is the infrared thermal radiation from dust here, and then in the radio broken up by synchrotron and free emission, I think. So for the most part, what you're measuring is free, but if you're in this little window, you just have to pay attention to what wavelength you're measuring to make sure you're getting your radio. You can also use H alpha instead of FUV. So H alpha is another star formation rate indicator. Most H alpha emission is going to come from hydrogen that's getting radiatively excited by light from young stars. So there's a few steps there. Young stars put out high energy light, that high energy light bumps into hydrogen and we see H alpha emission. So that's the Balmer transition, and 2 to 3, I think, electron transition in hydrogen. You get a slightly different time scale. So that's what's kind of showed here. If this bump down here is kind of, every time there's a bump, there's a burst in star formation. And this is looking at the difference between H alpha and FUV light. And so what we can see is right after a bump in star formation happens, we get a spike in H alpha and then a spike in FUV. So H alpha, FUV, and then they're pretty constant. And then right after the star formation happens. So you're getting different time scales of star formation if you're using different indicators. The nice thing about H alpha, there's a lot of hydrogen. So it's a fairly bright line. It's pretty easy to observe. A lot of observatories have a H alpha filter. The con is that it's still an optical emission line, so it still gets blocked by dust. So will still need to be corrected for dust extinction. Let's do, okay. These might have to wait, but I do, there's kind of a few other star forming laws that we can talk about that I'll throw those into next class since we are pretty much out of time, and just encourage you to maybe take a few more minutes. If you're, depending on where you are, if you're having total issues, even getting programs to run, for whatever reason, that's fine. We'll figure that out. But I would encourage you to try to work through this star formation rate measurement, because this is aperture photometry and that is your main homework assignment, is doing this. If you have questions, I have office hours on Monday from 10 to noon, but I'm also happy to meet with you outside of that time if that doesn't work. And then again, we can turn these in just by submitting those notebooks and I can see how you're doing. And if you do get to a point where you're just banging your head against the wall, don't do that. Either let me know you're having an issue, look at the solutions and see if you can work it out from there, or submit what you have and say, I didn't finish, but here's what I've got. Can you tell me where I'm going wrong? Like, that's also fine, any of those options. But again, yeah, this is similar to your homework. This is pretty much what extragalactic astronomy is aperture photometry. So doing this is pretty essential. Otherwise, I think that's all I have. I'll stick around if you have questions, and have a good weekend.
Thank you.
Thank you.
Thank you.
Thank you.
I guess I'll ask my question.